Hello viewers, welcome to this lecture on coordinate frames. In this lecture, we shall see how the position and orientation of a coordinate frame with respect to another coordinate frame can be expressed in the form of a matrix. So, this concept is very important in robotics because it is very essential to know the position and orientation of a robot with respect to its environment or with respect to various objects associated with it to perform a particular task. So, first before going into those details about robotics, we will concentrate on coordinate frames. So, first let us introduce some basic notations and definitions. So, the 3-dimensional space R3 is defined as R3 is the set of all 3 tuples x, y, z, where x, y, z are real numbers. So, the space R3 is denoted by this thing. So, any point in this space, any point P can be written as the coordinate x, y, z, and the point origin O is nothing but having the 3 zeros in the bracket. So, the coordinate of the origin is 0 0 0 and coordinate of any point P is x, y, z, and we can interpret this as if you drop a perpendicular to the xy plane, it meets the xy plane at M, and if you drop perpendicular to the x axis from M, it let us say it meets at L, and if you drop perpendicular to y axis, it meets at N. So, we can say that OL is x, ON is y, and PM is z. So, any point P is represented by a coordinate x, y, z with respect to this particular frame. The directed line segment OP is called a vector here. P is called a point and OP is called a vector. Now, if you consider the directed line segments from O to 1 0 0, 0 1 0 and 0 0 1, these 3 points, they are called the vectors I, j, k, and they are called the basic vectors or the standard basis of this coordinate frame. And it can be easily seen that any vector R represented by this point x, y, z can be written as x into I plus y into j plus z into k. In other words, x into 1 0 0 plus y into 0 1 0 plus z into 0 0 1, that represent the point x, y, z. The magnitude of the vector R is the length of the line segment OP, which is given by square root of x square plus y square plus z square, which can be easily seen from the geometry. If the magnitude is equal to 1, then that vector is called the unit vector. So, now let us see meaning of dot product and cross product. So, if A and B are 2 points with coordinates x1, y1, z1, x2, y2, z2, and the corresponding vectors are A and B, then the dot product between A and B is denoted by A dot B equal to the length of A into length of B multiplied by cos theta, which also can be obtained by the expression x1 x2 plus y1 y2 plus z1 z2 in terms of the coordinates of A and B. So, here the theta represent the angle between the 2 vectors. So, here we have x, y, z axis. So, if you have 2 vectors A bar and B bar, then if the angle between them is theta, so the dot product can be written in this way. So it also says that if we take modulus of A, the length of A into cos theta is the projection of the vector on the vector B. So mod A into cos theta is the projection and mod B is the length of the vector. So the product of the two is the dot product between these two. We can also observe that if modulus of B is 1, then A dot B gives the projection of the vector A on the unit vector B. The cross product A cross B is expressed or defined by the determinant as given in this expression. So when we expand this determinant, we will get the I component is y1 z2 minus y2 z1 plus j component k component as given here. This also can be proved that this expression is same as mod A mod B sin theta multiplied by the n vector, where the vector n is perpendicular to both A and B vector. So if these are two vectors A and B, then the n vector is the unit vector perpendicular to both A and B vector. And how it is defined, this n vector, there are two perpendicular vectors to A and B. So that is using the right hand system. So that will be explained in the next slide. So we see that if the dot product of two vectors is equal to 0, then they are perpendicular to each other, that is seen from the formula directly. A dot B is mod A mod B cos theta. If theta is 90 degree, then A dot B equal to 0. So the vectors will be perpendicular to each other. So or we call them as orthogonal vectors. If the modulus of both the vectors are 1, perpendicular vectors are 1, then they are called orthonormal vectors. The standard basic vectors I, j, k, it forms a right hand system. So the right hand system is, if this is I 1 0 0 and 0 1 0 0 0 1 vector, then if the right hand fingers curl from the I vector towards j vector, then the k vector is pointing in the direction of the thumb. So that is why the system is called the right handed system. So whenever we consider a coordinate frame, it should be a right handed system. So instead of the standard ijk vector, we can consider any three unit vectors f1, f2, f3 which are mutually perpendicular to each other. So if they form a right hand system, then we call it as a coordinate frame. So for example, to become a coordinate frame, f1, f2, f3 should satisfy this condition, f alpha dot fn equal to 0 if alpha is not equal to n, and f alpha dot fn is 1 if alpha equal to n, where alpha and n are constants. Alpha can be 1 2 3 and n also can be 1 2 3. So these three vectors satisfy this two condition. It means if alpha is not equal to n, they are perpendicular to each other, and if alpha is n, the length of the vector is 1, that is indicated here. So in the place of ijk, we can use any three mutually perpendicular vectors. So let us say f1, f2, f3, these are three mutually perpendicular vectors. We can call with the same origin O, then we call this also as a coordinate frame. Now we consider how to represent the position and orientation of one coordinate frame with respect to another coordinate frame. So let us assume f1, f2, f3 are mutually orthonormal vectors. That means they are orthogonal and the length of each vector is 1. It forms a coordinate frame, a right handed system. Similarly, M1, M2, M3 form a coordinate frame. Then any point P can be expressed with respect to F1, F2, F3 as well as with respect to M1, M2, M3. So, we will see how these two representation of the same point in both the systems are related. So, this result says that if R is a vector in the space R3, then if R is represented in terms of F, that is related by the same vector R represented in the space M by multiplying a matrix R here. So, the relation between R with respect to F and R with respect to M is related by this expression, where R is called a rotation matrix here. So, because we can obtain the M frame by making a rotation with respect to F frame suitably, so that the R is called the rotation matrix and the relation is given by this expression. So, we will see how this R matrix can be obtained from F1, F2, F3 and M1, M2, M3. So, we can write this relation R as F or M, because we will express the matrix, the coordinate frame M with respect to F frame. So, this notation means F or M is the representation of M with respect to F. So, ultimately we get the relation x1, y1, z1 is the coordinate of the vector R with respect to F frame, and x2, y2, z2 is the coordinate with respect to M frame. Then they are related by this expression, where R is this matrix given by this expression. So, how to prove this relation? Because the point P x1, y1, z1 can be written in the form R is equal to x1 f1 plus y1 f2 plus z1 f3, because R is represented in terms of f1, f2, f3. Similarly, R can be written in terms of m1, m2, m3. The corresponding coordinates are x2, y2, z2. So, it can be easily seen from here. If I take the dot product both sides with f1, and we know that f1 dot f1 is 1, f2 dot f1 is 0 and f3 dot f1 is also 0. So, we will get R dot f1 is x1. Similarly, R dot f2 will be y1, R dot f3 is z1. So, R dot f1 is x1, R dot f2 is y1, R dot f3 is z1. Same way here it is using m1, m2, m3 mutually perpendicular vectors. So, we will get R dot m1 is x2, R dot m2 is y2, R dot m3 is z2. So, now we want to see the relation between x1, y1 is z1, x2, y2 is z2. So, that can be seen directly from here. We can write the vector R, because x1 is R dot f1 etc., and in terms of m1, m2, m3 it is this expression, this is x2, y2, z2, and mi or m1, m2, m3 these are also vectors in the F frame. So, the mi vector can be written as, if you replace R with mi, we get here mi dot f1 into f1 plus mi dot f2 into f2, mi dot f3 into f3, I equal to 1, 2, 3. So, this this is obtained by replacing r by mi vector. Now, if we substitute this mi value in this expression, if you call this as say one equation and this as equation 2. So, if I substitute this equation 3 in equation 2, we will get r bar to be like this, directly substituting and collecting the coefficient of f1, f2, f3 from after the substitution here. So, we will get the expression to be r bar equal to, in terms of f1, f2, f3, if we collect the coefficient we will get this expression. So, this can be directly seen. To prove this one, here we have x1 equal to r dot f1. Now, we can write this f1 in terms of this m1, m2, m3. So, this can be written as f1 dot m1 into m1 vector plus f1 dot m2 into m2 vector plus f1 dot m3 into m3 vector. So, this is the expression. So, this gives r dot m1 into f1 dot m1. This is nothing but if I take dot product with r and m1 into f1 dot m1. The second is r dot m2 into f1 dot m2 plus r dot m3 into f1 dot m3. So, the value x1 is written like this. Similarly, the value y1 can be written as r dot f2. In the place of f2, if we substitute this expression, we will get, wherever f1 is there we will replace it with f2, and similarly z1 we get the similar expression. So, from this 3 equation we will get x1 is written as m1 dot f1 into x2. We know that x2 is nothing but r dot m1 and y2 is r dot m2 and this is r dot m3. So, this is what we get from this expression r dot m1, r dot m2, r dot m3. So, what we get here is the coordinate of the vector r with respect to f frame and the coordinate of the same vector r with respect to m frame are related by this expression. So, if you observe the first column of this matrix F R M, the first column is nothing but the coordinate of the vector m1 with respect to f1, f2, f3 coordinate frame. Similarly, the second column represent the coordinate of the m2 vector written with respect to the f1, f2, f3 frame. So, the 3 columns are simply the coordinate of the m1 vector, m2 vector, m3 vector, and we know that these 3 vectors are mutually perpendicular and the length is 1. So, the matrix represented by this expression is a orthogonal matrix. What is an orthogonal matrix? If A is a matrix such that the columns, let us say C1, C2, C3, the columns are such that the length of each column is 1 and the dot product between any 2 column is 0, then that matrix is called orthogonal matrix, is orthogonal matrix if we take For example, the A transpose A gives you the identity 1 0 0 0 1 0 0 0 1. So, it can be easily seen if A transpose is the inverse of the matrix A, then it is a orthogonal matrix. So, same thing happens here because the 3 columns are mutually perpendicular and they are of length 1. So, the vector F or M between any two frame F frame and M frame, it is a orthogonal matrix. But the converse generally is not true. Every rotation matrix is a orthogonal matrix as given here, but every orthogonal matrix need not be a rotational matrix. Here for example, if we take 1 0 0 0 0 1 and 0 1 0, it is orthogonal by the definition. A transpose A is identity, but here we can see that this will not form. The first column represent the x axis, for example 1 0 0, the second column represent the z 0 0 1, third column is 0 1 0, this one. So, if we rotate from the first to the second column, then the thumb should be pointing towards the third one, but it is pointing in the opposite direction. It will not form a right hand system, okay. It is not a right hand system. It is not a rotation matrix, so it is not a So, for example, if F is a coordinate frame with I, j, k as the coordinate axis and M is another coordinate frame with the first axis as j, second is minus I and third is k. This will form a right hand system. Now, if you give a point P with respect to the M frame as 0.6, 0.5 and 1.4, then what will be the coordinate with respect to the F frame. So, we can make use of the formula as we shown here, this expression. With respect to M frame values are given, we want to find the values with respect to F frame. So, here M1, M2, M3, it is given as j minus I k, this one. So, we can write the j is 0 1 0, minus I is minus 1 0 0 and k is 0 0 1. So, this is the M, this is F or M as given here, and multiplied by this we will get the coordinate with respect to the F frame. It is a simple example to illustrate. Now, the fundamental rotation matrices. Fundamental rotation matrix is as follows. If we rotate about the x axis by an angle theta, then we can see that the x axis will remain the same, but y and z axis will be shifted to this position. So, we can see that the length 1, because this length is 1 here, we get the projection of this is cos theta. So, the x axis will not change, the y value has become this expression. The y coordinate has come to this expression. Here it is cos theta y value and z value is sin theta. And here we can see that it is x value is same because it is in the y z coordinate. Z axis has shifted to this position OW. It is in the y z plane. So, the coordinate of this W point is x is 0, y value is minus sin theta and z value is cos theta. So, if you write this in the columns, the first column is 1 0 0 only, because the axis is the same for the first initial frame, and after rotation also the x coordinate is 1 0 0, and the y axis is given by 0 cos theta and sin theta. So, that is in the second column. The third column is 0 minus sin theta and cos theta, that is given here. So, this represent the fundamental rotation about the x axis by an angle theta. Similarly, if we rotate about the y axis by an angle theta, the y axis will not change. So, the second column is as it is 0 1 0, but the x and z axis will change its position like this thing. Cos theta 0 minus sin theta will be the coordinate of the x axis after rotation, and z axis after rotation the coordinates are sin theta 0 cos theta, the unit vector in the z direction. So, similarly the rotation about z axis can be written in this expression. So, these three rotations are called the fundamental rotations. Now, using this fundamental rotation we can obtain any general rotation. So, here we see another example, a point alpha u v w is given. So, we have two coordinate system x y z coordinate system. After rotating it has become u v w coordinate system. So, here it was obtained by rotating 60 degrees about the o z axis. So, we have x y z axis, and if you rotate 60 degrees about the z axis we get the new coordinate frame like this. We call it as u v w frame, because we are rotating about z axis, w is same as z axis. So, now the point in the u v w frame is given as 432, and what will be the point with respect to the original xyz frame. So, we can make use of the rotation matrix, because it is rotation with respect to z, the fundamental rotation matrix can be obtained. This is cos 60 and minus sin 60 and sin 60 cos 60 calculation can give the expression like this. Okay. Now, the composite rotation matrix. So, here we note that if you are performing successively various rotation operations. So, if you have initially a fixed frame, a frame with the coordinate frame f1, f2, f3, then we make some kind of rotation and then we obtain a new coordinate frame. So, let us say m1, m2, m3 frame. So, we call it as m frame, and then we again make a rotation with respect to m frame and we obtain a new frame, let us say m1, m2, this is m1 m frame, and another frame capital M1 frame with 3 coordinate axes. So, first we had a frame f that is fixed, after that we made a rotation, we got m, again we made a rotation with respect to m frame, then we obtained a new frame m1. So, what will be the relation between the f frame and then m1 frame? So, the orientation of m1 frame with respect to f frame is called f or m1. So, that is obtained by just multiplying f or m and then m or m1. the orientation of M1 with respect to M frame, and then we pre-multiply the orientation of M with respect to F frame. So, that will give the representation of M1 with respect to F frame. But the other scenario is, if first we have the fixed frame F and then we make a rotation with respect to the F frame and we got a new frame M. Now, we make again a rotation with respect to F frame itself, with respect to F frame, and we obtain the M1 frame. So, this is different from the previous step. We are making, in the previous one we are doing the rotation with respect to the current frame, whatever is the present frame we are making rotation with respect to that frame itself. So, then we have to multiply in the right hand side, that is post multiply. But if we make rotation with respect to the base frame every time and obtaining a new frame, then the relation between the first F frame and the last frame is given by the. So, if we make, for example, the rotation 1 some operation with respect to F frame and obtain the M frame, and then if we make another rotation with respect to the base frame and obtain a new frame M1, then the relation between M1 frame and F frame is obtained by pre-multiplying the operation successively. So, in this result we have shown that we have R with respect to F frame, it is given by F R M and R with respect to M frame. Now, if we make a rotation with respect to M frame and obtain a M1 frame, then the relation between M frame and M1 frame is obtained, and the coordinate of a point in M1 frame is related by the coordinate of the point in M frame is given by this expression, by the same theorem, replacing F and M by M and M1. Now, if we substitute this R M from the second equation, we get, so the coordinate of the vector R with respect to F frame is F R M, and M R is written as M R M1 into M1 R. So, this implies that R with respect to F and R with respect to M1, they are related by F R M1. So, F R M1 is nothing but F R M multiplied by M R M1. So, similarly, if we make a rotation with respect to M1, then we have to multiply in the right hand side. So, in general we have, if we get from F, if we take M and from M we get M1 and then M2 etc. Mk. After k steps we come to a coordinate frame Mk, then what is the relation between F and Mk? That is given by F R M1, F R M and M R M1 etc. Mk minus 1 R Mk. So, by successively multiplying the right hand side we get the relation. This is for the rotation with respect to the current frame. Similarly, we can show if we do the rotation every time with respect to the base frame, then we can obtain, we have to pre-multiply the rotation at every step. So, this concept will be very useful in understanding various coordinate frame related concepts in robotics. So, that we will see in the coming lectures. Thank you.